Okay, we are now recording. Let's go from current slide. But let me make these couple of announcements. I think I've made them all before. Everybody knows about the student course evaluations, right? And you're going to do them if you haven't done them already, right? Good deal. Okay. You have until August 8th. Don't wait till August 8th to do them. Do them while you're thinking of it. Once August 8th gets here, you're not going to think about any of this anymore at all, I don't think. Okay. Now, this is the adjustment to my office hours. It's really been happening for just about every Tuesday and Thursday. Monday and Wednesday still the same. I'm here from 8 to 8:30, and I'm here from 5:30 to 6. Okay, on Monday and Wednesday, that's all the time I've got. I'm in class from 8:30 to 5:25, except for little bitty breaks here and there. Okay, but Tuesday and Thursday, according to what I announced at the beginning of the term, 10:45 until 4:30. I was supposed to be here on this campus most of that time. However, the last several Tuesdays and Thursdays, and for this coming tomorrow and next Tuesday, I've been having to go, and I've got to go again to the Birmingham campus sometime in the afternoon. On Thursday, I'm going to have to leave no later than 2 o'clock, okay, to get there because I've got a meeting at 2:30. On next Tuesday, I've got to leave no later than 1 o'clock because I've got a hearing at 1:30. So for the next two, for tomorrow and for Tuesday, my office hours on this campus are shortened to 10:45 till 2 and 10:45 till 1, respectively. After that, as far as I know, I'll be here from 10:45 until around 4. I'm going to try to start leaving a little before 4 because it's hard to make it there in half an hour, every time. I can sometimes I can't, so I don't want to be late for that next class that starts at 5, so I'll leave a little before 4:30. All right. Any questions on anything before we get started, what we did for today? Any questions on what we've done so far? All right. Now, we're in Chapter 10, which is conics, which we talked about. You're not going to be tested on. Parametric equations, that's what we're doing now, and we'll get to polar coordinates. Okay? We're on page 740 in Chapter 10, Section 10.2, Plane Curves and Parametric Equations, and this is top of page 704, Finding Parametric Equations. In case you lose them, this is how you... No, I'm sorry. Okay. And they jump right into the example. Okay. Find a set of parametric equations that represent the graph of y is equal to 1 minus x squared using each of the following parameters. And I hate it they told you what to do. Okay. Here's how I approach this. Find the more complicated variable. What would that be here? One that has more mess with it. Between x and y. Which is more complicated? Second? The x. Set that equal to your parameter, t. So let t equal x. Okay? Then plug that in, and what is your y? Y minus t squared. So t is equal to x. I don't know what this is doing, but that's the first thing. Let t equal x, and then I would have written it the other way. X equal t, y is equal to 1 minus t squared. That's a set of parametric equations that represent that graph. Okay. And then it says, using each of the following parameters, the slope m, which is dy dx at each point of xy. Well, what is dy dx? So let m equal negative 2x. Okay, so there's the second one. Okay, the first one, I would have written it, let me get my pen set up. Now this may not be exactly how they're meaning to do this, but this is what I'm interpreting. I would write this as x equal t, and y is equal to 1 minus t squared. There is your set of parametric equations that represents that graph. Now this one, your m is equal to, as you said, minus 2x. So that's your parametric equation, okay? Rather bizarre how they did it this way, but if m is equal to minus 2x, then that implies that x is equal to minus m over 2. Now plug that in here and you get y is equal to 1 minus a minus m over 2 squared. And that would be 1 minus m squared over 4. So there would be your second one. Either written like that or written like 1 or 4 minus m squared over 4. Either one of those would work. I don't know why they chose such a weird representation, but that's what they did. They left it in this form here. So I'm looking ahead to see. Yeah. Okay. So why would they go to the trouble of doing such an awkward representation like this when that was so straightforward, so easy? But the point being, I think you could say an infinite number of parametric equations you could use to represent that function. Okay? Some of them pretty simple, some of them not quite as simple. Okay? But let's see how they did it. They told you what to do, so they should tell you how to do it then. So, if you first let t equal x, let that be your parameter, then that means, of course, x equal t. So there's your first parametric equation. Then plug that in to this one, and you get 1 minus t squared. There's your second parametric equation. X equal t, y is equal to 1 minus t squared. That's the easy way to go, folks. Okay? Now, the B part, to write x and y in terms of the parameter m, you can proceed as m is equal to dy dx, which happens to be, why they went to very small print, I don't know. M is equal to minus 2x, which you got from taking the derivative, dy dx. And then that gave you x is equal to minus m over 2, which is exactly what we did. And then plug that into your original function, y is equal to 1 minus x squared. So plug that in here, and you get y is equal to 1 minus m over 2 squared. That gave you y is equal to 1 minus m squared over 4. Now, a word of warning. At this stage here, it's really tempting to say, well, minus times minus is plus. But that's not what you're doing here. It's minus an x squared. Just because that's a minus, you square it first before you subtract it from that. By squaring the negative m over 2, you then get a positive m squared over 4, and that's then the minus that makes it 1 minus m squared over 4. A really bizarre choice of parameters, but certainly just as good, I guess. It's just a lot more sort of stranger, okay? But the point is, you can have almost an infinite number of parametric equations to represent any given equation. Okay. I think they're going to show this graph. Yes, they do. If we had done our first one, the function looks just like that. Okay? when I say the first one, this one, x equal t and y is equal to 1 minus t squared. Okay? Okay? If you had done that one, I'm going to do this in a different color. Someone give me a different color. Pick a color, any color. Anyone? Second? Blue? Okay. Light or dark? Dark. Okay. We'll do that dark blue. So we're going to first do this one. X equal t. Y is equal to 1 minus t squared. Give me a t. 0. I love it. What's your x value? Second? 0. And what's your y value? 1. Okay, there we are. Same place. Okay? It just won't draw. Okay, there we are. Okay? Give me another t. 1. What's your x value? X equal 1. Y is equal to 0. 1, 0 is down here. So by that first choice, our function is going this way. Okay? By the second choice, the one they're showing, the points are the same. I could just plot every one of those points just with different choices of your t. But you see it's going that way as you increase the t. But with this choice, okay, you'll notice here, same points, got to be the same points, the same graph, okay? But here, your m equals 0 gives you x equal 0, y is equal to 1. So there it is, m equals 0. But m equal 1, what does this do? Negative 1/2, and this would be three-fourths. Okay? Negative 1/2 would be here, 3/4 up here. You're going this way. So that's why their arrows point in this direction. Because you see you're going in the opposite direction. What gives it away is your x is negated here, the other one that wasn't. So you're going positive there. So, same points, same graph, same everything, except they're going different directions. Okay? And basically at different speeds too, because with m here only gets you 1/2 to 3/4. So that's not moving quite as fast as we're going from 0 to 1. Okay. For part A, the curve would have had the opposite orientation, but also different spacing between different values. So me? Oh, good, okay. All right. I have been known to pull my computer onto the floor. I didn't think something like that. Notice ours is t is equal to 1, t equals 0, t equals 1. This is m equals 0, m equals 2. M equals 1 was somewhere up here. So what I'm saying is you're not getting there as fast. Okay. In some sense. Okay. So that's example 4. Any questions on 4? Example 5. Okay. And by the way, at the bottom of page 704, there's a other methods of finding parametric equations. There's an article finding rational parametric curves of relative degree 1 or 2 by Dave Boyles in College Mathematics Journal. You certainly can, if that's what interests you, you can go for that. Okay. 10 point on page 705. Now, they're introducing a concept here. Determine the curve traced by a point P on by a point P on the circumference of a circle of radius A rolling along a straight line in a plane. Okay? So if you picture this, doesn't matter really where you start. If you start with the A down here, as the wheel turns, this picks up, gets to the maximum, comes down, touches here, goes up and down, up and down. That is called a cycloid. Okay? As the wheel's turning, that goes. Oh, okay. It says determine the curve traced by a point. I sort of artificially drew it for you. Not for folks at home, they couldn't see that. You could. But let's us pick a parameter, and a good parameter would be theta. What we're wanting to do is give the equations of a curve, the parametric equations of a curve. So let the parameter be theta, because as it's moving along, the angle of this line to that point is increasing as you curve, as you go around. So theta, not a bad choice of your parameter. Let the point P, x, y, begin at the origin, and that's where I said we would begin. Okay? So let's do, when theta equals 0, P is at the origin. So if you think of that, your circle is here, it's down here, so the angle is between where it's starting here, and as it turns, this point, as the wheel turns, this goes like this. So your angle is going to be changing. I hope they show a picture of that because it's hard to describe this way. When theta is equal to pi, okay, the P is a maximum point, and that maximum point is going to be, theta is along this way, and you've gone, not really, I wish I showed a picture of it. It's pretty obvious to know you're at 2A now. You started down here, you rolled up to here, okay? Think of the line here, and you've rolled along until it's up here. So you've gone an angle of pi, so your y value is 2A. It was down here 0, now it's 2A because the radius A. Now, it's gone pi times A this way, okay? That's not quite as obvious unless they give us a picture here. When theta is equal to 2 pi, you've rolled all the way around until it's back down again. So this should be twice as far here, but you're back down at 0 here. Okay. Please, all right, here's the picture. All right. Now, you started here. You're pointing downward. 0, theta, 0, everything. As you roll, your theta has gone from 0 to pi. Here you're pointing downward, here you're pointing upward, so that's a total of pi. Now, how far did you go along the circle? Move this back here, so here's your pxy is down here. How far did you go this way? The x coordinate here, you went exactly, for x, half of a circumference. Because if you think about this, when this point was down here, that's where you started. And as it's rolled, then this point was on the bottom, then this point on the bottom, this point on the bottom, till there. And when you get to this point, the point exactly opposite here is on the bottom. So you have rolled in the x direction half a circumference. Okay? That's why I wanted the picture here so you can see that better. Half a circumference. Well, the circumference is 2 pi r, or 2 pi a. So you've gone half a circumference, which is pi a. And, of course, when you roll all the way around, your x value is 2 pi a. You've gone one complete circumference on the x-axis, but you're back down at 0 here. So here's your max up here. Now, this is called a cycloid. Now, how you get these parametric equations, okay? And here's your key. Save other, but no. All right, pretty good attendance today so far. Hopefully some more will be coming in. Okay. They say from this figure, if you look at this, you started with an angle of 0, you're going to an angle of 180 here. Why they went to degrees, I don't know, but I wish they'd have gone. See, down here they're calling it pi, and up here they're calling it 180 degrees. Get your act together. This isn't making sense this way. But it's still okay. Okay, this angle theta, you started down here, and you're going, at this point you've rolled up to here, so you've gone 180 degrees. So your angle APC, and A, I assume, is this point here, PC. Oh, okay, sorry. That's angle APC. The angle theta, that's what I was really interested in. Theta, it was 0 here, and it's on the way to 2 pi. By the time it rolls up here, I mean, it'll be pi by the time it gets up here, okay? So that's going from 0 to pi. Now this angle here, APC, is this one right there, and that angle is, if you subtract 180, which will be up here, subtract your theta from that, here's 180. Subtract theta from that, you get this angle here, which is inverse, alternate inverse angles, interior angles from here. So that would be this angle APC. Now, why are you interested in APC? Okay? They don't make that completely obvious here, but it's true. And to keep from having to do this at enormous lengths here, this winds up being your parametric equation with the parameter theta and your x's and y. X being this way, y is that way. Okay? Certainly when theta is equal to 0, this is 0, that's 0, x is 0. So that's making sense so far. And since we know this point is on there, let's make sure this one's there. When theta is equal to pi, okay, sine of pi is again 0, so a times pi. That certainly works. And let's see about this one down here. When theta is equal to 0, cosine of 1 minus 1 is 0, so sure enough that point is there. And when theta is equal to 180 or pi, then cosine is minus 1. 1 minus a minus 1 is 2, 2a, sure enough, that's your value there. Plug in another couple and you see these work. Doesn't show you how they got them, but at least it shows you they work. Now, before we get into too much detail here, the little blurb on the left says Galileo first called attention to the cycloid, once recommending it be used for the arches of bridges. Okay? Not a bad idea. Pascal once spent 8 days trying to solve many of the problems of cycloid. And Pascal was a really sharp dude. Took him 8 solid days to try to solve some of these problems. So don't feel like if these look a little wacko to you, they did to others, many good mathematicians. Such as finding the area under one arch, finding the volume of a solid revolution, blah, blah, blah. Cycloid has so many interesting properties and has caused so many quarrels among mathematicians that it has been called the Helen of geometry or the apple of discord. I've never heard that before. I saw it here. If you want more information, they give they reference an article here if you're interested in going there. Okay, now, they give in the book how they got these, and I just as soon not have to go through all that, but the book gives a pretty good solution to how they got there. Okay, it uses this thing, the observation that the angle APC is that, and it goes through and solves a whole bunch of kind of weird things, but they do come up with that. Now, here's what I want to point out about this. The cycloid here has smooth portions to it and very sharp portions there. These are called the cusps. Okay? They're places where the smooth curve comes down and abruptly makes a very big change of direction. Corners do this like an absolute value function. They do the same thing. This is even more pronounced. That's called a cusp. So obviously it's differentiable in here, but not there, because the derivative coming in this way and the derivative coming that way, not the same. This is going to infinite, negative infinity. This is going to positive, coming from positive infinity. So very big discontinuity of first derivatives there. Between the points, the cycloid is called smooth. Okay? Now, okay, they're showing, okay. Using this here, they're going to show you how they got these derivations. That's good. I didn't want to have to go through this. So keeping in mind that the angle APC is 180 degrees minus theta. I would have said pi minus theta, but it doesn't matter. Everything will work out all right. Whereas this is your angle theta. This is your angle of your, this is your parameter. This angle theta is your parameter. The angle APC here is that value is 180 minus theta. Okay, so with that in mind, here's what they do. The sine of theta is also the same as 180 degrees minus theta, or pi minus theta. Because sine of 0 and sine of 180 are the same. Okay, which is the sine of the angle APC. Now, let's go back and look at that. The sine of this angle right here, by definition then, is opposite over hypotenuse. Well, hypotenuse is A. Well, what is this opposite side here? Shame they don't give it, okay? It's the length of D minus B here, okay? So I don't know how they're doing this. It's the length of D, dB, divided by A. But they also say it's the length of AC divided by A. Well, of course, dB and AC are the same. So yeah, that's the same. So the sine of APC is the same as sine of theta, okay? And sine of APC, yeah. And that is this thing over A. A is the, okay, either AC over A or BD over A. All right. Now, the cosine, let's go to do that one. Cosine of the angle theta. Okay, cosine of theta is going to be, now how does that relate? Since theta, 180 minus theta is this angle here, and the cosine of that would be the opposite side. Oh, I'm sorry, this angle. Cosine of that is the adjacent here over hypotenuse, which is A. Well, that would be AP. over A, just to keep it short. AP over little a. I can't see because of the glare. Oh, I'm sorry, over negative A. The reason for that is it's really minus the cosine of it is what they're getting at, because the cosine of 180 minus theta, if you go back and do your cosine formulas, you'll find out there's a minus sign in there, and that's where the minus comes from there. It's one reason I didn't want to go into this. That's the AP over minus A, which implies that AP is equal to minus A cosine theta. BD is A times sine theta. It's just from multiplying this by that and this by that. Okay, so you get those two. Now, let's go back and look at what those AP and BD are. Okay, AP is this one, BD is this one down here. Okay. All right. Because the circle rolls along the x-axis, you know that OD is equal to, what do they mean by PD with a, this is why I didn't want to get into this. OD is the arc from OP, okay? Because this is what's rolled along here. So the arc here that goes from, not I'm sorry, I said here. This arc here is exactly what OD was. That's what rolls. So the arc from, and here's golf. All right, great. We're only missing Corey, not here yet, and Taylor. Taylor, by the way, did come by yesterday too. So, all right. So that's what they're saying. This is here is also OD is this arc DP. I hope that's what they said, because that's what the truth is. Yeah, PD. Okay, and that's also A theta. Okay. I hope you remember that too. The arc of an angle, measured in radians, by the way, not degrees, and that's why it irritates me they use 180 there. In radians, that is the arc cut by that is the radius times that angle in radians. That's how they define radians. It's the ratio of the arc divided by the radius. That's how many degrees radius. So the arc is the radius times the angle. So that is A theta. All right. Furthermore, because BA is equal to DC, let's go back to that. I wish I had it. Which did I say? BA is equal to CB, is that what they said? BA is equal to DC, yeah, and that's equal to A. You have X is equal to OD minus BD. They just define both of those. That's A theta minus A sine theta. And that's where they get your first parametric equation in theta. A is fixed, theta varies, okay? And Y is equal to BA plus AP, which is A minus A sine theta, okay? A cosine theta, okay? All right. So the parametric equations are those. X equal A theta, A times theta minus sine theta, and Y is equal to A times 1 minus cosine theta. Okay. So this cycloid has sharp corner called cusp. and that the derivatives of x prime as a function of theta. In other words, dx d theta is perfectly defined, okay, but they're both 0 at the points where theta is equal to 2n pi. And that 0 over 0 is not one that will reduce that. It's indeterminate, but it's not going to give you a derivative. Okay, so between those 2 points, the cycloid, not cyclone, cycloid is smooth. So here's the definition of a smooth curve. I thought we were going to do this at some point. A curve C represented by x equals f of t, y is equal to g of t, on an interval I is called smooth when the f prime and g prime. Now, when they have the primes here, this means df dt and g dt. Okay? When both of those are continuous on that interval I and not simultaneously 0, except possibly at the endpoints of the interval, which in this case they were. The curve C is called piecewise smooth when it is smooth on each subinterval of some partition of I. And so each partition would be in between those angles that give you the cusp. All right. That was example 5 in gory detail. Now, they're only going to talk about these things because they're really interesting, but they're really complicated. And I don't even know how to pronounce them correctly. The tautochrome, I think is how you say that, and the brachistochrome. Does anyone know a better pronunciation than those? Have you run into those ever? Okay. You're fortunate until now. Okay. The cycloid is related to one of the most famous pairs of problems in the history of calculus. The first problem, called the tautochrome problem, began with Galileo's discovery that the time required to complete one full swing of a pendulum is approximately the same whether it makes a large movement at a high speed or a small movement at a slow speed. Now this runs out at past certain angles, but if you just started the pendulum at A to B, it would go back and forth, and its time is the same as if you started at C to, let's just call it C prime over there. This would be moving more slowly, this would be moving more quickly, but the time required to go back and forth is the same, which is sort of fortunate. Because where do we see pendulum a lot? Or you used to. Did your granddad have one? Your grandfather's clock? Okay. Or grandmother, yeah. You get those doing. Whether you do a big arc or a small arc, the time is going to be the same. Okay? That was what Galileo discovered, and that because of this tautochrome, what they call the tautochrome problem. Okay? Galileo realized that you could use this principle to construct a clock, which he did. However, he was not able to conquer the mechanism of an actual construction. He was a good physicist, but probably not good of a machinist. Okay. Now, Christian Huygens, I think that's how you pronounce his name, much later than that, was the first to design and construct a working model. He realized that the pendulum does not take exactly the same time to complete swings of various lengths, but it was close. But in studying his problem, Huygens discovered that a ball rolling back and forth on an inverted cycloid does complete each cycle in exactly the same time. So rather than the arc of a circle, which is what a pendulum describes, the curve on a cycloid, it would. Okay? The second problem, which was posed by John Bernoulli in 1696, is called the, this is even worse, brachistochrome problem. In Greek, brachis means short, chronos means time. The problem was to determine the path down which a particle will slide from point A to B in the shortest time. Okay? And the solution is not a straight line from A to B, but the inverted cycloid, passing through the points A to B. That's the shortest time this will do. Straight line will not be the shortest time. So the shortest distance, but not the shortest time, because it starts going more slowly here, because its component, due to gravity, is less than here. You know, this is really great. It gets it moving quickly and then evens up and beats the ball going down the straight line. Okay? This inverted cycloid does it for you. Okay? Interesting, perhaps, maybe useful in some circumstances, but not the easiest things to deal with. Okay? That's all they do. Oh, wait, I'm sorry. The amazing part of that, of the solution of the brachistochrone problem, is that a particle starting at rest at any point C on the cycloid, inverted cycloid between A and B, will take exactly the same time to reach B as if it started here. So if you started here, see, it has very slow speed to start with, so it takes the same time to get there as it does if it started here, which has a faster speed, and of course keeps going. And this one's even faster. They all take the same time, no matter where you start. Okay? And that goes back to Galileo's, it doesn't matter what the arc is. So if your pendulum, or whatever you're using, could follow an inverted cycloid, then that would be a very precise clock. Okay? Same time to reach point B if you start at A, C, wherever you start. Pretty amazing. That's all for 10.2. Homework exercises include any of the odds 5 through 21. They're all at Calc Chat. 13's at Calc View. Any of the odds 23 through 33, they're all at Calc Chat. 25's at Calc View. Any of the odds 30, either 35 or 37, they're both at Calc Chat. 39 or 41, they're both at Calc Chat. Any of the odds 43 to 49, they're all at Calc Chat. 51 or 53, both at Calc Chat. 53's at Calc View. 55 or 57, both at Calc Chat. 55's at Calc View. 59 through 65, they're all at Calc Chat. 67 or 69, you can explore doing those if you like. Think about them. They're should be at Calc Chat. There's some matching problems here. It would sort of be fun to do all of those, even though the answers for only 71 and 73 would be at Calc Chat. 75 should be at Calc Chat, and either 77 or 79 are true-false, and they should be at Calc Chat. 81 is a projectile motion problem. It should be at Calc Chat. It's a baseball problem. Okay. And then there's a section project on cycloids. And this gets back to our Etch-a-Sketch. Okay. It looks like they do at the very bottom of that page. So let's move on to 10.3, which is parametric equations and calculus. Oh, or is that why we're doing this? Okay. All right. What did I just do? I don't think I did the right thing. 10.3. Didn't go to the right one. Okay, PowerPoint will start at some point. This is a fairly long PowerPoint, not as long as the last one. Okay, here we go. Start from current slide. And that, by the way, is Jake swinging the bat. No, I'm just kidding. Okay. So, he's chasing down the fly ball. All right, okay. Parametric equations and calculus. Our objectives here are to find the slope of a tangent line to a curve given by a set of parametric equations. We'll find the arc length of a curve given by a set of parametric equations. And we'll find the area of a surface of revolution in parametric form. Okay? Which is pretty much related to the arc length, but we'll see. So let's start with slope and tangent lines. Okay? Consider a projectile represented by the parametric equations. X is equal to 24 root 2 times t. Now that t is not under the radical. Okay? That's why I like to write it as 24t root 2. Even though you split up the number, you don't have the confusion of whether it's under the radical or not. Because when I write, my lines don't always stop where I want them to. Whereas y is equal to minus 16t squared plus 24 root 2t. T is outside the radical there too, as shown in this figure. Okay? You know that these equations enable you to locate the position of the projectile at any given time t. Now, quite often they use t as your parameter, and it doesn't have to have anything to do with time. These, it just happens that it does have to do with time. Okay? Now, you also know that the object is initially projected at an angle of 45 degrees. That's the initial angle of projection. And the slope is m is equal to tangent of 45, which is your initial slope, is also is tangent of 45 is 1. Same as pi fourths. All right. So that's, they just came up with these two equations. Now these two equations probably have a lot more meaning than you would think, but they haven't gone into what those meanings are. It seems like we did a problem with them earlier, so you may recognize them. But how can you find the slope at some other time? So in other words, they're saying, you know the slope initially is 45, but how about later? It's not going to be 45. Because it's curving downward. This is part of a parabolic flight here. Okay? So your angle is decreasing up to a certain point. Okay? So how do you find the angle theta later? Okay? Next theorem answers that question by giving a formula for the slope of a tangent line as a function of time t. In this problem, t is time. Parametric form of a derivative. If a smooth curve C, we just had there, is given by the equations x is equal to f of t, y is equal to g of t. Remember this one was 24 root 2t, this was minus 16t squared plus 24 root 2t. Okay. Then the slope of C at any point xy is given by dy dx, which happens to be dy dt divided by dx dt. That sure looks like it should make sense, right? Given that dx dt cannot be 0. Okay? So you can't have the slope of the x ever be 0. So f prime can never be 0 within the interval that you're in question. All right? So let's do it. Find the y dx for this curve. How do you think you will proceed? Where would you start? Would you start? How about dx dt? That's equal to cosine t. Good. And dy dt equal to negative sine t. So what would be your dy dx? Negative sine t divided by cosine t, which is equal to negative tangent t. Okay? Now, hopefully they'll draw a picture for you so I won't have to. Okay? One little thing wrong with that problem, though. Anyone notice what it is? Your answer especially. They're saying dy dx, but you're given the answer as a function of t, not x. Whereas most of the time we sort of want that to be the case. So I'm not sure it's really worth it, but you could go back and visit with t is equal to inverse, t is equal to the inverse sine of x. So this would be minus the tangent of the inverse sine of x, which would be really, really awkward. And they don't do that. Thank you very much. Okay? It just seemed bizarre, but they left it as minus t. So I think, all right for me to erase. I think you'll see they did the same thing we did. Solution dy dx is dy dt over dx dt, whereas dy dt was minus sine t and dx dt was cosine t, and they just came out minus tangent t, and didn't bother with the fact that's not in terms of either one of the variables mentioned above. All right. Now, because dy dx is a function of t, you can use theorem 10.7 repeatedly to find higher order derivatives. Because that's a function of t, so you can just do it again and again and again. So d2y dx, which is just d by dx and dy dx was a function of t, so you can take that as derivative with respect to t divided by dx dt, okay? Because you're taking partial with respect to x again, so that would be partial of x with respect to t, okay? And then just do it again, because this winds up being a function of t. Then take the derivative of that with respect to x, which is taking the derivative of this thing with respect to t, and this thing with respect to x. Okay, but this is you just do dx dt again in the denominator, and this is a function of t. So that's how you do these. Hopefully you won't have to often. The first derivative is pretty simple. After that, they do get a bit more complicated, though the actual doing of them doesn't look as bad as this. Okay. But let's see. They're skipping example 2, aren't they? I was afraid of that. All right, let's do example 2 here. All right. For the curve, x is equal to the square root of t, y is equal to 1/4 of t squared minus 4, where t is greater than or equal to 0. Any reason why that is put in there? Is that just arbitrary? T has to be greater than or equal to 0. Chose to put it in to make the problem easier. What you think? Oh, you can't take the square root of a negative number, so t had better be non-negative, greater than or equal to 0. No, it wasn't arbitrary. It was essential. Okay? All right. It says find the slope and concavity. So we will need second derivative at the point 2, 3. So how we go about finding the slope? Second? Okay. dy dx, is that what you're saying? Or the others? Oh, okay.
Don't you take it like each individually and divide by 2?
Say that one more time.
Don't you do like dx, dt?
Okay, let's do that. Okay, before I take dx dt, guess what I want to write it as? Yes, t to the 1/2. That's far easier to take a derivative of. So what now is dx dt? One half t to the negative 1/2. Okay, and dy dt is equal to, all you really need is that first term, 1/4 t squared. What would that be? Derivative of that? 1/2 t. Is that what you said? Okay. And then what? Dy dx would be 1/2 of t over 1/2 of 1 over the square root of t. Now I'm going back to my radicals. Not that I like them that much, but I think it's a little easier to see. The good news here, the 1/2s go out. They've been dating. No, I'm just kidding. Okay, so this will be, actually, I take that back. This is easier to do if you leave it as t to the minus 1/2. Why did I change that? Second? Okay, yeah, but before you do, what can you simplify that pretty quickly? Same base, different exponents, divided t to the second 3/2, is what you said? Perfect. So there's your dy dx as a function of t. Okay? Now, and that's also a very convenient form to do as you, okay. First they said, find, for the curve defined by this, find the slope and concavity at the point 2, 3. So what's your m at 2, 3? The slope at 2, 3. What would that be? You got another issue there, sort of, don't you? You need to find out what value of t that is. So let's start with this one and say that, doesn't that imply the first one here, let me go up here and do it, that t is equal to x squared. So that would be for the point at 2, 3, that would be t equal 4. Let's see if that works for the y value as well. Y at 1/4, yuck. That's not what I wanted to do. There's what I wanted to do. Okay. Y at of t, well actually, I think it really was what I wanted to do. Y at 4, when t is equal to 4, would be what? 1/4 of 12, which is 3. And sure enough, that's your y value. x2, y3, that's at t equal 4. Okay? So what's the slope at that point? Be, yeah, 4 to the 3/2 power. What's the square root of 4? 2 cubed is? 2 cubed is 8. Okay. Okay. So 8 is the slope at that point. M is equal to 8. Good deal. Now, let's go back to where we were And to do concavity, we'll need to know d2x y dx squared, right? Which they just told us would be d of dy dt divided by dx dt. Okay? That's what they had above, right? Now, we need to do derivative of dy dt. Well, I'm sorry, that's a dy dx. It's d by dt of dy dx. Strange but true, okay? Okay. So our dy dx is this. Take the derivative of that with respect to t. And what do you get? Derivative of that with respect to t. 3/2 t to the 1/2 divided by dx dt. We've already done that. Here it is. 1/2 t to the minus 1/2, right? And here your 2's can go out, and that leaves you 3 t to the what power? To the first power. 3t is your derivative. So let's plug in t equal 4 again. That's the t we had. And what is that? So d2y dx squared at 2, 3 is equal to 12, which indicates it's concave what? Up. Positive concavity means, positive second derivative means it's concave up. And when you look at that, you see it is indeed really concave up. Greater than 0, it's concave upward at 2, 3, which you can see there it is. All right, that was example 2. Let's see where they go next. They go to example 3. There was a little more at the bottom of that page. Because the parametric equations x equal f of t, y is equal g of t, need not define y as a function of x, it is possible for a plane curve to loop around and cross itself and do all sorts of things. At such points, the curve may have more than one tangent line, as shown in the next example. And that's this one. A prolite cycloid, okay, given by 2t minus pi sine t is x, and y is equal to 2 minus pi cosine t. Now, sort of look kind of like a cycloid, and we had a thing variable here and here, but this was a little different. That things are a little bit different, and sure enough, it comes out that way. It crosses itself at the point 0, 2. It's just that coming in this way, the slope is there, and then when you come up this way, the slope is here. Okay, so you have a different slope when t is equal to minus pi halves, and you have t is equal to pi halves, even though it's at the same point. Okay? Now, find the equations of both tangent lines. So we're looking for the equation of the tangent line at those 2 points. Okay? So guess what we're going to do first? Yeah, let's do dx dt, and that's going to be 2 minus pi times cosine t. Is that what you got? Okay. And dy dt is equal to pi times the sine of t. Is that right? Yes. Because minus and minus is plus. Okay. Now, what we need next is dy dx, which is going to be now that looks like a big boo-hiss to me, okay? But we need that dy dx at two different places. We need it same point, 0, 2, but we have to figure out what the two possibilities are for our t's. Two different t's, same point xy, but two different t's. So let's go up to this one and find out what the first one, when x is equal to 0, is equal to 2t plus pi. Yeah, I think I want to do the other one first this time. Is that all right with you? I want to start with the y's on this one, because you only have one value of t. So y happens to be 2 is equal to 2 minus pi cosine t. Now, just a little bit of looking ahead just a tad. Pi is a coefficient of cosine t, and the odds are t is going to be expressed in some form of pi. So, can't swear to it, but I bet you will. Okay, so we have pi's being used in maybe a couple of different ways here. Well, first you can subtract off 2, so we have minus, subtract the 2 from both sides, and that leaves us minus pi cosine t is equal to 0. Okay? Now we're going to need at least 2 t's that make that true. Can anyone think of one of them? Okay. All right. If you divide by minus pi, both sides, that'll make things a little easier. And that just gives you cosine t is equal to 0. And what did you just say? T is equal to pi halves or negative pi halves. Now, those may not be the right two. We do know they are because they just showed them down here. But those are 2 t's that produce the there. Let's check and see if both of those will make this equal 0. We know they make that equal 2. Will they make this equal 0? So when t is equal to pi halves, say, this will be pi minus, what's sine of pi halves?
0.
Really? 1. So you have pi minus pi is equal to 0. Sure enough, that gives you an x value of 0. So let's do the minus pi halves and see if that will work. When t is equal to minus pi halves, this will be a negative pi minus pi times, what's the sign of negative pi halves? Negative 1, so that would be plus pi minus pi plus pi. Sure enough, is 0. So yeah, we got the zeros in both instances there. So 0, 2 is on it. So that's how we know that one of these is t is equal to minus pi halves, the other is equal to pi halves. We should have looked at the picture to see, but I wanted you to see how to do it. Okay, so those are the two values for t. Now, giving those two values, let's now calculate the derivative. So let's do the first one at what you want to do, positive or negative pi halves? Positive. So we'll do this at pi halves. Okay, so we'll plug that in and you get pi. And what's the sign of pi halves? 1. Okay, so the numerator is 1. The denominator is 2 minus. And what's the cosine of pi halves? 0, so that'll be 2. So your slope at pi halves will be pi halves. Okay? Slope at pi halves will be pi halves. That's pretty interesting. Okay? And that gives you, that makes this the positive one over here. Okay? Slope is positive. So dy dx at x equal minus pi halves, no, at t equal minus pi halves, will be pi times sine of, so that'll be a minus 1, and your denominator here will be 2 minus pi times 0, so this will be minus pi halves. Okay? And sure enough, that will be, there's your slope there. Okay? Interesting enough, what the t value is also the dy dx, even though they're not related that much. Okay? So with that in mind, we need an equation of both tangent lines. Now, what do you need to have an equation of a tangent line, or equation of any line? You need two pieces of information. And a intercept? Yeah, an intercept will certainly work, and you lucked out that you got an intercept in this case, didn't you? Okay? A point and a slope was the broader answer. If the slope if the point happens to be an intercept, you're really in good shape. Okay? So what we have for the first one is y is equal to what? Second? Okay. Y is equal to mx plus b, right? Right? And m is pi halves. Pi halves times x plus 2. Okay? And down here you get y is equal to negative pi halves plus 2. Okay, same y-intercept. Okay, so there are two equations of the tangent lines. All right, let me see if that's what they got. Now, why in the world did they write them this way? They wrote it as y minus 2 is equal to minus pi halves x, and y minus 2 is equal to positive pi halves x, which is exactly what they got. We got, but they didn't put them in a very standard form. Okay? All right. That's example 3, prolate cycle. Any questions on that? Okay, the next slide, oh, here's carrying on. Oh, showing how they did it. Because x equals 0 and y is equal to 2, when t is equal to plus or minus pi halves, which is exactly what we found out, dy dx would then be the same form we got, pi sine t over 2 minus pi cosine t. You have dy dx is equal to minus pi halves when t is equal to minus pi halves, and plus pi halves when t is equal to plus pi halves. Don't expect the model to work out that way. They won't. I promise. Okay? So the two tangent lines are y minus 2 is equal to minus pi halves x, and y minus 2 is equal to positive pi halves x. Why not write it y is equal to minus pi halves xt plus 2 and positive pi halves x plus 2? I don't know. Okay, now arc length is starting sort of a new type process, but we're at the point we usually take a little break. Y'all want one? I could definitely use one myself. So let me pause the recording here, a week from Tuesday, so hopefully I can get a pair of glasses that they won't be straining all the time. But let's see. Okay. Arc length. Hopefully you remember back in single variable calculus how we did arc length. Here it is in parametric form. Okay? I'll try to make a little bit of a connection here. If a smooth curve C is given by f of x, x equal f of t, y is equal g of t, such that C, the curve, does not intersect itself on the interval a to b. Okay? Now, t is going from a to b. Remember that last example we had one that did intersect. To do arc length, you can't have that happening, okay? Because things get all screwed up. Now, it can intersect itself possibly at the endpoints because they don't cross. They just come to the same end, okay? But as long as they don't intersect themselves on the interval a to b, and this is interval of t, not x or y, okay, then the arc length of C over that interval is given by, and S is what they use for arc length now, the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Now, or written in this form, integral from a to b of the square root of f prime of t squared plus g prime of t squared dt. Now remember, these are the limits on t, not on x or y. Now, quick flashback to arc length in single variable calculus. This was not a t then, this was an x, okay? And these were, if you think about it, if this were an x here, these would be x's, and dx would be 1, and 1 squared is 1, plus dy dx squared dx. That's exactly the formula. It would be 1 plus the first root of the square. Or, flip these around then, we were used to saying f prime squared plus 1. But then the f is this and not this one, but you get the idea. So yeah, that's so similar to what the arc length was before. Hopefully it's not that hard to remember. It's the same type principle. It's, you think of any sort of little line segment that would represent that, that's dy dx, this is dy dt, dx dt, some of those squares would be the arc length. Okay? Pythagorean theorem, basically. That's what it looks like, that's what it is, but there are derivatives in there, squared. Okay? If a circle rolls along a line, of course it would, okay, then a point on its circumference will trace the path of a cycloid. Yay, we've been there before. If the circle rolls around the circumference of another circle, then the path of the point is called an epicycloid. Okay? Now, why are they focusing so much on these kind of things? But this is what an epicycloid looks like, and this is our example 4. A circle of radius 1. Oh, this is your circle of radius 1. Notice the diameter is 2, but the radius is 1, because this is 1, 2, 3, 4, 5, 6, you know, so radius of 1. Rolls around the circumference of a larger circle of radius 4, as shown in this figure. The epicycloid traced by a point on the circumference of the smaller circle is given by, just pull this out of the air or some other unknown body part, x is equal to 5 cosine t minus cosine of 5t, y is equal to 5 sine t minus sine of 5t. Yeah, we would know that, okay? Now, here's where you're going. You're starting here, you're beginning to roll. Now this is one circle rolling, they just showed it in 4 different things. It rolls up here, right about here at 45, you're going to get the peak distance away, then rolling on, and touching here, and then starting the process again, and again, and again, okay? That's your epicyclone, okay? Now, it says find the distance traveled by the point in one complete trip around the larger circle. Now, if you happen to think, let's just go back and use this formula right here, either one of these, it's the same one, and do that and go from, say, let's see what they, t equal, this would be going from here to there. That would be the same point as there, there, there. So it has made is that pi fourths or pi halves? Hasn't gone all the way around. But anyway, you don't try to do all of those. Just do one of them because of symmetry, multiply it by 4. Now, one of the reasons you don't try to do them all is these derivatives are not continuous at these points here, at the, they call those, I can't think what you call them. Not corner, but whatever you call those points. I want to say spur, that's not it either. But anyway, not continuous. So what you do is go just from here to here, and then multiply that by 4. That will save you having discontinuous first derivatives. Okay? So, but what you got to figure out is what I was just fiddling with. Find the distance traveled by the point in one complete trip around the larger circle. And they've shown you the picture, show it's 4 equal nodes, 4 equal lobes here, and I guess they call those nodes. Okay, so they come to a point. So 4 equal lobes, and just do one, multiply it by 4. Now, the question is, what is your angle there? Because basically it's the angle T, okay? And T starts off here. So this point right here goes to there, there, and there. So I guess it does do say that angle is 0. That one's got to be pi halves. So I think that's where you're going. The T is 0 to pi halves, I believe. Let's see if that's right. Before applying theorem 10.8, notice that, that figure 1033, that the curve has sharp points when T is equal to 0, pi halves, 3, pi, 3 halves, pi, at all those points. So you don't have clean derivatives there, Okay? So what you do between those points, the dy and dx are not simultaneously 0. Okay? Let's see. Here your dx will be 0, but dy is not. Did I say that right? Dy would be 0, but dx is not. Up here, the x would be 0. Well, dx is undefined. And so, yeah, but at no place are they both simultaneously 0, as you see, sort of following the circle as it goes. So that's the second element. Between the points, they're never simultaneously 0. So the portion of the curve generated between 0 and pi halves is smooth. That's the key. You can only do this on the smooth portion. To find the total distance traveled, then do the arc length of that portion in the first quadrant, multiply it by 4, because those appear to be and are exactly equal. Okay? So we do our integration 4 times, because we do it, from 0 to pi halves of the square root of the x dt squared plus dy dt squared, and then integrate that over dt. So, what do we got to do first before we can solve our problem? Do a dx dt, and what would that be? Minus 5 sine t plus 5 cosine 5t. Okay, what's your dy dt? Five cosine 5t. Oh, sorry. It was supposed to be sine. That's how we got the plus sign. We took the derivative of cosine of minus sine. Okay. All right. And what do we do with those? Okay, wait. That's the previous.
We add them.
Square them and add them and then take a square root. Okay, so let's do those in some sort of order here. Let's just change this to x prime squared. Is that okay? Don't have to write as much. Ooh, and what would that be? Squaring a binomial. 25 sine squared t minus 20, isn't it? It's twice the product of the two. Okay. Wait, 50. Wait. Product would be 25. Twice that would be 50. Okay. 50 sine t sine 5t. Right? Messy, messy, messy. Next, plus 25 sine squared 5t. Okay. That's messy, right? Hopefully it'll get a little better. Let's do y prime squared. What would that be? 25 cosine squared t minus 50 cosine t cosine 5t plus 25 cosine squared 5t. Now we're going to add those two together. Since they're running right over each other, can we just add them?
Yeah.
Okay, and what do you get?
25 sine squared t plus, do not add the whole entire thing.
Okay, well what's 25? Factor out the 25, and what do you have? Sine squared t plus cosine squared t. That's 1. So this will be 25, right? All right. Now this one will get messy, but let's factor out what we can. Minus 50 times sine t sine 5t plus, because I have the minus out front, cosine t cosine 5t. And then the next one, plus 25 again. Okay, so this actually turns out being 50 minus 50 times that mess. Sine t sine 5t, okay, plus cosine t cosine 5t. Seems like there should be some identity that can make that easier to do. But anyway, you could write that as 50 times 1 minus sine t. Let's see. Let me clean this up a little bit. It's hard for me to write, and it's hard to see what I've written. Factoring out the 50, you have 1 minus yeah, I was going to have to do the minus across both of them. Minus sine t sine 5t minus cosine t cosine 5t. Running out of room rapidly. Okay. Now what you got to do with that is take a square root, right? You've added those two squares together, take a square root. Now, the square root of 50 is 5 root 2. Okay? So let's go back to the next page, and if I can remember how to write those things. All right. So this arc length will be 4 times the integral from 0 to pi halves. And this is t's now. And this will be the square root of, let's see, let's pull out the, what do we say? 5 times root. So 5 root 2 will go in front. So that would be 20 root 2, right? Because you had a 4 out there, and multiplied by 5 root 2 would be 20 root 2. I hope I'm doing this quickly. Okay. Okay. And what you have here is 1 minus sine t sine 5t minus cosine t cosine 5t dt. Now that looks pretty miserable, doesn't it? Unless you recall, and back when I taught trig, I said you seldom use these. Okay? I'm trying to remember if these formulas are in the front of your book or not. I don't recall that they are. Yeah, wait, hold. Ha, here we have it, I think. Let me make sure. Yeah. If you look in the front inside cover of your book, if you have sine u, sine v, that's 1/2 cosine u minus v minus cosine u plus v. And cosine u cosine v is 1/2 cosine u minus v plus cosine u plus v. So with that in mind, let me try to do this. 20 root 2. Now they didn't pull out the root 2 like we did, but it's okay. 0 to pi halves. Okay. The square root of 1 minus. Okay. I'm going to write down exactly like they do here. 1/2 cosine, and they say u minus v. Okay? That would be a minus 4t. Right? Minus cosine of u plus v, which would be 6t. Okay? Minus, doing the second one, 1/2. Let me close off that one. 1/2 cosine of a minus 4v again, 4t again. I can't spell right or whatever. Plus cosine of 6t. Now, there may be a part of you say, that made it any easier? Let's see. Hope I did them right. Okay, this is a minus a 1/2 of a cosine of minus 4t. And by the way, cosine is what kind of function? Even function. So cosine of minus 4t is the same as cosine of 4t. So here you have minus 1/2 of cosine of 4t and another minus 1/2 of cosine of 4t, and that would be minus cosine of 4t. So this would be 20 root 2 integral from 0 to pi halves of the square root of 1, okay, and these two add to be minus cosine of 4t. But look at what happens to this next one. Minus, a minus is a plus cosine 6t, and minus a plus is a minus cosine 6t, and those add to 0. So this is what you got, dt. I've been leaving off my dt's, but they're still there. Delirium tremens. No, I didn't say that. Okay, now, is that something we can integrate? Perhaps, but they're loving our trig functions today, aren't they? If you go back to your page on trig, and you see the, I think it's called the half angle formulas, okay? They don't quite express them correctly here, but if you look at what they call the power reducing formulas, inside cover of your book, they say 1 minus cosine 2u over 2 is sine squared u. Okay? What we have is a 1 minus cosine 4t. So let u be 2t. So that would then be a 2u, right? And that would be 2 times the sine squared of 2t. Okay? So let's write that. 20 times the square root of 2 times the integral from 0 to pi halves. We're not changing the t. That'd be the square root of, okay, I'm going to have to write this down because otherwise it gets lost in the sauce. Okay. Sine squared of 2t is equal to 1 minus cosine of 4t, I'm changing it ever so slightly, over 2. Okay? So what we have here is multiply both sides by 2, and you have exactly what we've got here. So 1 minus cosine 4t is 2 times the sine squared of 2t. Now, dt. Get out of there. Okay. Now I'm beginning to regret like crazy I pulled out my root 2. It was legal to do way back when we did it. But, I don't even remember when it was we did it, but at some point we did it. If we put that back in here, that then is the square root of 4 sine squared of 2t, which happens to be what? 20 times the integral from 0 to pi halves of 2 sine 2t dt. Okay? Believe that's right, right? Now, the other thing we could have done was factor out the root 2 and put it out here, which now I wish we had done. That would have been a little easier. Because I got to get, well, no, I don't. Do I? I'm not sure. Let's hang on for a minute here. Let's not move too fast. What would be that antiderivative? Antiderivative of sine of 2t dt. What's that? Let's deal with the big function first. What's the antiderivative of sine? And negative cosine, okay. Negative cosine of 2t, right? But then we would do a sort of an anti-chain rule, and you would divide by 2, right? So the 2 will be wiped out by the 2, so I think that gives it to us exactly, and we'll evaluate that from 0 to pi halves. Okay, now, before I do that, I want to just make sure. Let's take the derivative of this. Derivative of minus cosine would be positive sine 2t times 2. Make sure that is what we have. So, yeah, that worked out nicely. As long as we come up with a positive answer. And it's not looking promising, is it? Oh, yes, it is. That would be 20 times. What is the cosine of pi? Because 2 times negative 1, but you got a minus there, so that's a 1, right? Okay. Minus, that minus, which makes it a plus, cosine of 0 is 1. Okay. Now that looks a lot like to me to be 2 times 20, which would be 40. Oh, can it be? Yes. That is your answer. Now, I don't, okay, we didn't do, see, I'm teaching Cal 1, 2, and 3. Did we do earlier in this course arc lengths, or was that Cal 1? Was it this course? Okay, yeah, so it was here. And remember I said to find formula equations that a function that when you take a derivative of it, square it, add 1 to it, take a square root of it, it gives you something you can integrate, few and far between, okay? Because that's a mess. Well, this time you're taking two parametric equations that when you take a derivative of each of them, square each of them, add them together, take a square root of that, you get something you can integrate. Lo and behold, that's why they picked such a weird example to begin with, because it happens to work out perfectly, okay? So it seemed at first I wanted to scream and say, why the first example you give us of these do you pick such a bizarre problem? But that's why, so you can get an exact solution that is integrable. Now, they give a little additional oh wait, let's just go and show what they do. All right, let me erase this, because I forget this is one they do show. Okay? All right. 4 times, and they took derivative of that. Oh, they just put it in parentheses squared. That was the derivative of that, just like we found. Squared plus the derivative of that, squared. All under the square root times dt. And from out of nowhere, they just pulled out a 20, okay? Actually, when you square everything here, you get 5, so 5 times 4 is 20. That's where that came from. They left the 2 in there, which now I see why, okay? But not having a crystal ball, you couldn't see it earlier. So that gave, and they just left out steps like crazy here. But remember, when you do square this, you get this, and square that, you get things. So those added together give you 1. So that's one of them. But then these will add together to give you 1. So that's where your 2 comes from. And then you have, which you pulled out the square root of 25, which is 5. You left with a 2 here, so that's where that 2 comes from, and the 2 there, and that's where that comes from. So everything is correct, what they did here, leaving the root 2 in there. We pulled that out and left this as 1s. Okay, now, at that point, they start calling on their trick, and they don't tell you exactly where they get it, but they say, this is the formula for cosine. That says nothing to me. It's your, what they used to call, goodness gracious, I had a name for it. Product to sum formulas. That's where those come from, or they used to call it that. This formula for cosine, I don't see it, but whatever. That's what you get, which is the same thing we did. So we had the root 2's out at that point. And that happens then to be, from your half-angle formulas, this expression. Leaving the 2 in there, that gave you a 4. When you pull that out, that gave you a 40 on the outside, because the square root of 4 is 2, 2 times 20 is 40, and then you just have sine of 2t. Antiderivative of that is, they pulled the minus sign out with the 20, cosine of 2t evaluated from pi halves to 0 to pi halves, and that would be, they don't show you any of the steps, say, it's 40, okay, fine. Okay. They're skipping an awful lot of steps here, but we did the same thing, a little more detailed, and got 40. All right, for the epic cyclone shown in this figure, the arc length of 40 seems about right because the circumference of the circle is 6. Now, why 6? Well, 6 would be if you took the circle that went all the way around here, 2 units out, that's the maximum it gets is 2 radii here, so it gets 6 there. Okay? Now, that circumference, you would think would be less than going in like this. And sure enough, it is, but not by a whole lot. And sure enough, the circumference of a circle of radius 6 is 2 pi r. 12 pi. Pi is about 3. 1.14, blah, blah, blah. So this is something a little bit greater than 36. 37.7 rounded. Okay. So yeah, that's a little bit shorter than 40. That seems like a very good answer. What a problem. All right. Now we're moving to area of a surface of revolution. Notice they're doing these pretty quickly with very few examples because you've done this type of stuff before in single variable. It's not a huge stretch here. So you can use the formula for the area of the surface of revolution in rectangular form to develop one in parametric form. So if you have a smooth curve C given by x is equal f of t, y is equal g of t, it does not cross itself on an interval a to b for t's, then the area S of a surface of revolution, now this one's really important, you don't cross themselves, because what would you have if you did an area of revolution of something that crossed itself? You'd have a mess and a half. So that would be really painful to even think about. So the area capital S. Little s is arc length, capital S is area of the surface of revolution formed by revolving that curve about the coordinate axes, either x or y axis, given by the following. Okay? Again, this isn't too far from what we did before. Remember, 2 pi r. Now, if you're going about the x-axis, okay, going around the x-axis, your y value is your radius, right, as you revolve around that. So the y value is g of t. So 2 pi r, that's how far it goes, and this is the arc length, that's that little segment that goes, this times dt is that little segment. So this is your arc length times 2 pi r. Summing all those up over all your t's, you've got it. If you're going around the y-axis, going this way, your radius is your x. Okay? So your x is your f of t, so 2 pi r, that's your how far that little segment of the arc length goes around there, and you sum all those up over your dt. And that gives you your total surface of revolution. Does that kind of make sense? At this point in the game, anything, no, or nothing, or never mind. All right, so let's see if we can do, well, wait. These formulas are easy to remember if you think of the differential of the arc length. ds is this thing, just what we did before. And then the formulas for theorem 10.9 can be written as 2 pi gs times the differential of the arc length. Okay, now, one thing that doesn't feel warm and fuzzy about this is that this is the variable t, and your a and your b are a reference to t, not referred to s. So this is a little bit of a problem here, in that, but you remember that the ds is referring to dt, so the dt does come back in here. But it looks strange if you are sensitive to how integrals are supposed to be. That sort of makes the skin crawl a little bit, but as long as you realize they're coming back in as a dt later. All right, so here's example 5. Let C be the arc of a circle. The circle is x squared plus y squared equal 9, and it's going from 3, 0 to 3 halves 3 root 3 over 2. Yeah, what a mess, okay? Well, first, 3, 0 obviously fits this, right? X equals 3, 3 squared is 9, plus 0 is 9. Does this one fall on that circle as well? Well, 3 halves squared is 9 fourths, plus, this again be a 9 fourths times 3, 9 fourths times 3 is 27 fourths plus, is that right? Yeah.
36 fourths.
That's what I got. Yeah, 20, yeah, 27 fourths plus 9 fourths. What did that come up with? 36 fourths and 32 fourths is time. Yes. The old gray cells got confused there a minute. Okay. So, C be that arc. Both of those are on the curve, so we're okay with that. It's shown in this figure. Find the area of the surface formed by revolving C around the x-axis. Okay. Now, from this point up to that point, and revolving C around the x-axis. So there you have it. A skull cap, or a beanie, or something like that over here. Okay? Now, okay. So what do we need to do to get this to work? Okay? Revolving around the x-axis, let's please probably not try to solve it in terms of x and y. Maybe a little bit better getting in terms of a parametric equation. Any parametric equation come to mind? All right. Now, if you haven't run into this before, let me encourage you to have a collision with it now. If you're dealing with radii and angles, okay, isn't this true? That the sine of some angle theta is equal to y over your radius. Yay or nay? Have you seen that before? Okay. And the cosine of that same angle theta is equal to x over the radius. Now let's rewrite each of those and do it this. Y is equal to r sine theta, and x is equal to r cosine theta. Now, have you seen those before anywhere in your past life? Yeah. Okay. Any of you taken any physics? Yes. Okay. You see those all the time there. So let's do the same formula here and square x. That would be r squared cosine squared theta plus, and y is r squared sine squared theta, and that's equal to 9. Well, guess what 9 is? 9 is your radius. So basically this is 9's not the radius, it's radius squared. So this is going around in a circle here. 9 is equal to 9, isn't it? Okay. So this is a circle. So basically, these are your parametric equations then. I've just proven that is true. 9 is equal to 9. R squared cosine, okay. That's the circle that we're dealing with, okay? So these are your parametric equations. Where R is a constant, theta is the variable. But what's theta going from and to? What's your angle theta when you're down here? 0 to pi, I don't think so. I'm sorry. Here's your theta here. And you're going to there. Theta equals 0 to theta equal . Okay, let's go to here. Here the x is r cosine theta. So 3/2 is equal to 3 times the cosine of angle theta. divide both sides by 3, and you got cosine theta equal 1/2. What angle theta would give you that?
60.
Second, 60 degrees or pi thirds. Okay, theta equal pi thirds. Right? Ha! Believe we can do. You can go back and check. I believe you'll find it works on the other one as well. Okay, so we've got our okay, everything should be in place now. So let's do our surface area is equal to 2 pi times the integral of, second, yeah, 0 to pi thirds. Okay. Okay. Remember here, yeah, your oh yeah, we're revolving around the x-axis, so it's your radius here is your y value, and your y value is r sine theta. So the r is 3, so that's going to make that a 6 sine theta times the square root of, oh, we got to do those, don't we? Okay. If r is equal to that, what's your, don't have much room, dy d theta. From this y. R is a constant, 3. Not that hard, is it? Yes, that would be 3 cosine theta. Okay, and your dx d theta would be negative 3 sine theta. Okay, and we got to square those, don't we? Remember, right here we're going to square each of those. Okay, when you square the first one, what do you get? It doesn't matter. Yeah, okay. Say that again a little louder. 9. Yeah, it doesn't matter which order. Cosine squared theta plus sine squared theta. Say again. Okay. Yes. Equal 9, actually, right? Oh, is it equal 3, right? Yes, okay. So you have another 3 when you pull these out. So I think that's gotten up to 18 pi now, times the integral from 0 to pi thirds of sine theta, d theta. Now the only thing I'm a little concerned with here is my d theta there, but I think that's all right. I believe we're okay there. Yeah. So what does this give us? 18 pi negative, oh wait, is that negative? Yeah, negative cosine theta, evaluated from 0 to pi thirds. All right, that would be 18 pi times, what's the cosine of pi thirds? Okay, so it'd be a minus 1/2 minus a minus, which is plus, and cosine of 0 is 1. So that's going to be, I think, 9 pi. 1/2. Where did it go? 9 pi. All right. Let's see how they did it. See, okay. Now, you can represent C parametrically by the equations, good old x equals 3 cosine theta, y is equal to 3 sine theta, as your theta goes from 0 to pi thirds. Note that you can determine the interval t by observing that t equals 0 and x equals 3, t equals pi thirds, and x equals 3 halves. Okay, I'm not sure I can determine that way, but I guess you can. I mean, it does work out. We checked it. Okay, on this interval, C is smooth and y is non-negative, and you can apply the theorem 10.9 to get the surface area, and that would be 2 pi times your y value, and your y being 3 sine t. You're going to integrate it from 0 to pi thirds, and then you have the they didn't show where you took dy dx and dx, I mean dy dt and dx dt, but that's what we got, just like they did. And pull out the 3 and go with this, make it a 6 pi. Then you have a square root of 9, which you can pull out another 3 and make it, well, they left it in there, fine for them. Yeah, and that's just a sine t. And then that gave us, now they pulled it out and made a minus 18 pi cosine t. Evaluate that from 0 to pi thirds, and that would be 1/2 minus 1, and that would be a 9 pi. Did it slightly differently, but came out with the same result. Any questions? All right, that ends 10.3. Homework exercises here include 5 or 7. They're both at Calc Chat. 5's at Calc View. Any of the odds 9 through 17, they're all at Calc Chat. 13's at Calc View. Either 19 or 21, they're both at Calc Chat. 19's at Calc View. Either 23 or 25, they're both at Calc Chat. 27 or 29, they're both at Calc Chat. 29's at Calc View. 31's at Calc Chat. Any of the odds 33 to 41 are at Calc Chat. 35's at Calc View. 43 to 47, all at Calc Chat. 43's at Calc View. 49 to 53, all at Calc Chat. 51's at Calc View. 55 and or 57, they're both at Calc Chat. 59 or 61, they're both at Calc Chat. 61, by the way, is talking about the folium of Descartes. So either who in the world was Descartes would be a decent paper topic. Speaking of which, I think I've gotten 2 papers in so far out of this, my best class ever. And you only got, what, maybe 1 or 2 weekends left? That's all, folks. Please get your papers done. Okay, commercial over. Where did I leave off? 43 to 47, all at Calc Chat. 43's at Calc View. Oh, no. 59 to 61, folium Descartes. Descartes would be a good paper topic. How he developed this folium and why he developed it, what it means, who uses it, any of those would be. 62, by the way, I think I've already mentioned the Witch of Agnacy. Agnacy would be a good paper topic, and how she developed this, how it got messed up with its name, who uses it, that kind of stuff. 63, any of the odds 63 to 67, all at Calc Chat. 65's at Calc View. 69 or 71, both at Calc Chat. 73's are writing, and so is 75's exploring. You can look at either of those. They should be both at Calc Chat. 77, the integration by substitution at Calc Chat. 79 should be at Calc Chat. 81 through 86, those are 4 shapes, and says you need a computer algebra system. If you do, you can skip this unless you happen to have access to one. Otherwise, you might be able to do them fairly quickly. But only 81 and 83 will have their answers to Calc Chat or in the back of the book. Actually, that's 81 to 85, any of those odds. 87 should be at Calc Chat. 89 should be at Calc Chat. 91 and or 93 and or 95. So any of the odds 91 to 95 should all be at Calc Chat. There's 2 true false, 97 and 99. They should be at Calc Chat. All right, let's end that one fairly quickly. And let's get started with 10.4. Now we started today, was that still in 10.2? I don't remember. I think we were.
Yeah, we started in 10.2.
Yeah, because that's where we had the cycloid and stuff, finding parametric equations. So we've done 10.2, 10.3, and now into 10.4. I say that so I'll remember how to label it at the end. Okay. All right. Still in Chapter 10, conics, we've already talked about. Parametric equations, we just finished. Polar coordinates, that's where we're beginning. So polar coordinates and polar graphs. We're basically going to deal with polar coordinates and probably not get too much into polar graphing. Okay? Now, if you need this in your majors, hang on to it and go back to it, but you'll still have access to it. Understand the polar coordinate system. Oh, yeah. Rewrite rectangular coordinates and equations in polar form and vice versa. Sketch the graph of an equation given in polar form and find the slope of the tangent line to a polar graph. Identify several types of special polar graphs. Okay? So let's start with polar coordinates. That's probably all we'll focus on now. So far, you've been representing graphs as collections of points x, y on the rectangular coordinate system. Corresponding equations for these graphs have been in either rectangular or parametric form. In this section, we'll study a coordinate system called the polar coordinate system. Okay? Have y'all dealt with this before somewhere or other in the past? Okay, so this is nothing new to most of you. To form the polar coordinate system in the plane, fix a point 0 called the origin, okay, or the pole. Origin, it was called also in the rectangular system, but it can be called that here, or the pole. Construct from O an initial ray, okay, called the polar axis, usually taken to be in the positive x direction, even though we're not using x, at an angle of 0. So the positive x-axis, okay? And then the they just sort of leave it hanging there, fix a point, and construct from O an initial ray called the polar axis, shown here. Now, what I'll show on the next slide, then do an additional ray that comes from the origin and has moved up. That additional ray has a fixed length, that's r, okay, or a variable length, that's a variable, r. That's your directed distance, the straight line distance there, and it's some angle theta from your polar axis. So r theta will now be your coordinates. R being how far from the origin, shortest distance from the origin, theta being the angle counterclockwise from your polar axis, which is the positive x-axis. Okay, not too much different from what you've done in physics, probably lots. Okay? Now, here's one little issue with it. Whereas in the xy system, you give me an x, give me a y, that's going to fix one point, and that will always be that point. Okay? Name the point, I can go straight to where that is. Okay? And it's the only name for that point. However, in polar coordinates, this point can be listed several different ways. One way, of course, is your angle theta here is acute or really obtuse, a big angle, same R, bigger theta, or go in the negative direction here, same R, negative theta, but a negative thing, another value, okay? And it even gets worse. If your R was negative, that means it's down this way, but given an angle that makes it go back here. So things can get really bizarre here, okay? That each point P in the plane can be assigned polar coordinates r theta, where r is the directed distance from the origin of the pole to the point P, and theta is the directed angle counterclockwise from the polar axis to the segment OP. So this shows 3 points on the polar coordinate system. This would be, usually your polar graphs, if you have them, will be a series of concentric circles. They'll still have what looks like an XY axes in them, but those are just so you can guide your angles. Okay, the concentric circles will be how far from the pole. So this is R would obviously be 2 because it's on the circle 2 units away from the pole. And you would be going up, this looks like about pi thirds. And by the way, the thetas are, I think, just about always in radians. I can't imagine ever doing them in degrees. I guess if you put the degree symbol, that would be readable and understandable. Most of the time we use radians. Okay? So that point would be called 2 pi thirds. Okay? Now, down here, you're on circle 3. Now, if you went counterclockwise, this point would be 11/12 pi. Okay? But if you go clockwise, the theta there would be minus pi 6. Okay? So 3 is by all means your radius, but you're either at 11/12 pi, no, I'm sorry, 11/6 pi or minus pi 6. Okay? And that's what they showed here. This is if you go around this way, you're 11/6 pi, but if you go this way, you're that's not right. This should be a plus right there, not a minus. Is that in your book? Yeah, it's in the book correctly, on the slide incorrectly. Okay, that's a, ooh, let me get my pen set up. It's a plus 11/6. Minus for here, because you're going clockwise. For here, since you're going counterclockwise, that's positive 11. We said it right here, but put the minus sign in there correctly. Okay. Sorry about that. Okay. So you see one difference between rectangular and polar coordinates. Any point on that has a unique set of coordinates. Not here, not on polar coordinates. They have to make sense, but they're not going to be unique. Notice that in this system, it's convenient to locate points with respect to a grid of concentric circles intersected by the radial lines through the pole. With rectangular coordinates, each point xy has a unique representation, not true for polar coordinates. That's what I was just saying. For instance, the coordinates r theta and r of 2 pi plus theta are obviously the same point. Okay? Or minus 2 pi plus theta. That would also be. Also, because r is a directed distance, the coordinates r theta and minus r theta plus pi represent the same point. Because minus r would be in this direction, but then you're if you go theta plus pi, that puts you back. So there's lots of different ways you can designate the same point. Not any old way, but they all have to be consistent. Okay. In general, the point r theta can be written as r comma theta plus 2n pi, where n can be any integer, positive or negative. Okay. Or the other one would be r theta would be the same as minus r times theta plus 2n plus 1 pi, where n again is any integer, positive or negative, and this makes the odd pi's, this makes the even pi's. Okay. Where n is any integer. Moreover, the pole is represented by 0 theta, where theta is any angle, which is a bit bizarre, but of course true. If your r is 0, you're there on the origin or in the pole. It doesn't matter what your theta is, because you're not going anywhere. You're taking a point and spinning it around. Okay, how are we doing? So, with that in mind, let's do what they call coordinate conversion. To establish the relationship, and some things are going to look very familiar here, between polar and rectangular coordinates, let the polar axis coincide with the positive x-axis. Yes, that's what we said before. And the pole with the origin. Yes. Okay? Because xy lies on a circle of radius r, has to, it follows that r squared is equal to x squared plus y squared. There is a conversion. If you know the xy coordinates, you know r. Because x squared plus y squared is equal to r. Moreover, for any positive r, now we're not doing the negative r's now, the definitions of the trig functions imply that tangent theta is y over x, cosine theta is x over r. These look familiar, don't they? Sine theta is y over r. You can show that the same relationships hold for r less than 0. You just have to fiddle with them some. So, especially here, this gives x equal r cosine theta, y is equal to r sine theta. So these two give you, if you know your polar coordinates, r and theta, you automatically know your x and y, just using those two. Now, this said if you knew x and y, you know r. This is if you know r and theta, you know x. If you know r and theta, you know y. How are we going to get, if you know x and y, do you get theta? Well, that's from this one, because the tangent of theta is always y over x. So, if you know the two rectangular coordinates, you know r and you know theta. If you know the two polar coordinates, you know the x and you know the y. Okay. So that's basically your coordinate conversions. So here, this theorem sums these up. Polar coordinates r theta of a point are related to the rectangular coordinates xy of the same point as follows. X is always r cosine theta, y is always r sine theta. So if you know the polar coordinates, you know x, you know y. If you know the rectangular coordinates, you know theta or tangent theta, just do the inverse tangent of this one, and you know the r squared, so take the derivative of that. So you know those are your basic conversions that you'll use lots. Okay, so here's example 1. Why did they show you the answer? Sorry about that. So, here you have r theta is 2 pi. What's your x value?
R cosine theta.
R cosine pi, right?
Right.
And what's cosine pi?
1.
Is it? Negative 1. So that would be negative 2. Got it. Okay. And what would be your y value? And what would that be? 0. Got it. So your x value would be negative 2, y value 0. Okay. Negative 2, 0. All right. right, so the rectangular coordinates are x, y is negative 2, 0. Why did they show you all that? Why didn't you? All right, so here's a point. R theta is equal to root 3 pi 6. What can you get from there? Don't read my arm. Okay. Say again?
So it's R cosine theta.
X is equal to R cosine theta, and your R is root 3. Cosine of pi 6 is?
1/2.
Okay.
No, 3. Yeah.
Second? Square root of 3 over 2. Square root of 3 times square root of 3 is 3 over 2. So that 3/2 is your x value. Your y is?
Root 3 sine pi over 6.
Okay. So root 3 times pi, and what's pi, sine of pi 6? 1/2, so that would be root 3 over 2. There it is. So your coordinate would be, your xy coordinates would be 3/2 root 3 over 2. And there you have it. All right. Here was the first one plotted here. R theta would be 2 times pi. Then put you over here, and sure enough, that's negative 2, 0. Your next one was root 3 was your radius, okay? And pi 6 would be how far up you go here. That would be 30 degrees, you know, a third of the way up between here and there. And that would be the point there. And there would be 3/2 here, and square root of 3 over 2 here. Square root of 2 would be 3 being a little bit less than 4, and 4 over 2, square root of 4 would be 1, so a little bit less than 1. And sure enough, that looks reasonably well. Okay. Any questions? All right. They're skipping example 2. So let's go back and do example 2. I think we have time. Okay. For the second quadrant point xy, they told you second quadrant, they should have been able to figure that out, is equal to minus 1, 1, yeah. Whereas x negative and y positive, second quadrant, so they have to tell you that, it's okay. Now, how could you get the polar coordinates for that point? Okay, how does that go? Tangent of theta is equal to, which is? Negative 1, is that what you said? And what would theta have to be then? Minus pi fourths, okay? Or you could go around and do a positive value if you wanted to, okay? That gives you the theta. We still need the r. What's your r? Okay, r is equal to the square root of x squared plus y squared, which is the square root of 1 plus 1, square root of 2. Perfect. So your polar coordinates of this one would be, your r theta would be root 2 negative pi fourths, which you could also write as root 2 7/4 pi. It doesn't matter which one you use. What did they use? Wait a minute. Something's a little bizarre here. Okay. This is something a little different with tangents too. I don't know if you know this. Tangents are positive positive in these two quadrants, negative in these two quadrants. So we did this one down here, negative pi fourths, which is the same as 7 pi over 4. But you see it's also true up here. So that could also have been 3/4 pi or negative whatever, you know. So there's even more possibilities here, okay? And the r would have been the same, root 2. So yeah. Wait. I'm sorry. God, no, wrong. This would have been 4th quarter. We needed to be in second quadrant, so that was important. They told us that. So that put us at 3/4 pi. So not 7/4 pi, but 3/4 pi. Sorry. You have to pay attention to the quadrants with tangent because you have two different quadrants you could be in. Always pi away from the other one. So that's 3/4 pi. Good deal. Sorry about that. All right. I think that was the A part. Let's see if we can do the B part quickly. Do we have time? Yay or nay? How much time we got? 3 minutes. Let's see if we can get B part done. Okay. Here's the point. XY is 0, 2. Okay. Where is that? Let's go and plot it this time. It's right up there, 0, 2. So what's that in polar coordinates? R is what?
90.
Second? 2, comma, pi has. Perfect. You can almost do that by inspection. You don't need to use any formula at all. See, we could get it done in 3 minutes, couldn't we, Jake? Huh? All right. Now, the question is, do we need to do polar graphs? If my memory is right, all they said was polar coordinates. And since we're running so short of time, what we'll do, I won't test you on polar graphs. I'll only test you on doing your polar coordinates, but we'll do a quick, if I can. I usually can't do it quickly. Slideshow of the rest of 10.4 and maybe 10.5. And real quickly on 10.6. Okay? It's a short section. Okay, because I'd love to get a little bit into 11. Okay, now, so we basically finished everything we need for chapter 10, well, 9 and 10. Remember, those two were together. And we got what? 1 week and 1 day left? Is that right? So let's just go on and combine 10, 9, 10, and 11. What we can cover in 11. I'll have all that on your last test. So you don't have the test now and then another test in a very short time. Is that all right with you? Okay. So we'll do that. I'll try to get that ready. The only trouble is figuring out how far to go in 11 before we get there. So do it the best we can. So we'll do a quick slideshow of 10.4, 10.5, and 10.6 that you're not going to be responsible for, and then we'll start into 11 next time. Now, is that okay with you, or would you rather have a separate test? 9 and 10, and then also 11. We can go either way. Any feelings? You okay with? All right, we'll go with it that way then. All right, let me escape here. Well, no, that's not what I want. I needed to end my